Okay, so although we see pendulums most often in a clock, that's where we see them and we think about them the most, a pendulum can be anything that's considered a mass on the end of a lightweight cord. Okay, there's two things that we have to pay attention to about the cord or the string that it's suspended on. It can't stretch. Okay, the length of that cord cannot vary. And we have to consider the length or the mass of the cord to be negligible. It's got to be a pretty lightweight cord, not enough to affect the gravitational pull that it's going to have basically on this pendulum. Okay, we can't have the cord or the string or whatever you want to call it be heavy enough to affect the overall period or frequency of that motion. Okay, we understand what a pendulum does, right? It just swings back and forth on a even, steady, repetitive, identical pattern, otherwise known as... If something, yeah, good. Simple harmonic motion or a simple harmonic oscillator. Okay, so a pendulum would be an example of a simple harmonic oscillator. Something that moves in repetitive, identical motion. Okay, for our purposes and for our equations, the length of our cord is going to be called L. Okay, and it should be measured in what value? Meters. It should always have a unit of meters. Okay. So before we jump into really calculating period and frequency based on the length of a pendulum, based on all these factors that go into a pendulum, we want to look at some simple calculations for frequency and period, okay? Just based on what we know the definition of a frequency and period are, okay? Frequency, remember, is the number of oscillations that something makes per second. Period is the number of seconds it takes per oscillation. So if we're given a number of oscillation and we're given the time it takes, we should be able to calculate those two things very easily. Okay, and so if you don't have your calculator out, please get that out now. We're going to work through just these very simple calculations for frequency and period before we move on to the little more complex equations for a simple pendulum. If we're going to solve for frequency, which we know is oscillations per second, what should the math look like that goes into that? Oscillations per second. 23 over 58. So if we want to find out the frequency, which is oscillations per second, we're going to take 23 oscillations over our 58 seconds. Okay, and that gives us a value of, what's that make our frequency? 0.49 something or 0.4?
0.3.
Everyone was yelling. Say it one more time. 0.396. Okay, so 0.4. I gotcha. Okay. All right, and what's our units then for frequency? Hertz. Okay. Or oscillations per second. Remember, oscillations are any complete cycle that goes back and forth. So any vibration that goes back and forth, anything that rotates all the way back and forth, any oscillation is a total back and forth motion. Okay, so we have the frequency of 4 hertz. Now when we solve for period, it's going to be basically the opposite of that, right? It's the number of seconds it takes per oscillation. So when we solve for t, we're going to take our 58 seconds divided by 23 oscillations. And that gives us what for our period? 2.52 seconds. Okay, and we just measure period in time in seconds because it's this many seconds per one oscillation. So you could make it over oscillations or make it over cycles or whatever you want, but basically this time is telling us this is how long it takes for it to make one complete back and forth motion. Okay, are we good with frequency period? Okay. So if we're given complete data like this, how many oscillations it takes in this many seconds, we're going to be able to solve using really easy math, okay, and not really difficult equations. Okay, now let's jump into our equations, our little bit more complex equations for frequency and period. Okay, these equations should look familiar to you, but we have two different variables. So instead of having our mass and our spring constant, we're going to look at the length of the pendulum and gravitational acceleration, or acceleration due to gravity. Okay, we're going to plug those in there. These are our equations to find period and frequency of a pendulum dependent upon its length. Okay, so as counterintuitive as it may seem, the mass on the end of this pendulum doesn't even have an effect on either the period or the frequency. You don't see an m anywhere in this equation. Right? So the mass of this pendulum has no factor. It doesn't slow it up, it doesn't slow it down, it doesn't speed it up. As long as we consider that the cord itself is massless and that the amplitude is not a crazy distance from equilibrium, we can consider using these equations. Okay, we can use the length and gravity to keep that in a simple, repetitive, identical motion. Okay, let's go ahead and try one here with frequency. So what do we do with the mass that they give us here in our problem? Yeah, we just ignore it. We don't need it. It doesn't fit into our equation anywhere. There's no reason for us to have it. Okay? So make sure that when you're doing these problems and doing them on tests or quizzes, don't let that throw you off, okay? Put in what your formula says you need. Don't try to make every number fit somewhere. Okay? Gravity. Regular 9.8. All right, so the order that we should solve this problem, we'll start by dividing this inside the radical first. Take the square root of that whole thing, multiply by parentheses 1, divide by parentheses 2 pi, parentheses. Okay, if you want to plug it all in one time into your calculator, I guess that probably takes 2 steps, but make sure that you're consistent in how you're plugging these into your calculator. Okay, what do we have? 0.42, and our units for frequency are hertz. Good. Okay. Does everyone agree? Do we get that to come out in our calculator okay? Yeah. Okay. Let's try another one here. Except we're solving for length of the cord instead of frequency. This is one that we'll have to manipulate our equation quite a bit. I'll probably do it with the numbers plugged in. Okay, so if you need to walk through the math to get this L by itself, please watch on the board or listen as we walk through it. Our first step will be dividing by 2 pi. Divide by 2 pi. Okay, so 0.98 divided by 2 pi is 0.155. That's still going to equal square root of L over 9.8. From there, our next step should be to square both sides, which gives us 0.024 L over 9.8. To get L by itself, we'll take that left side times 9.8. And that means the length of this cord should be about 0.24 meters. Do we agree? No? All right, so 0.24 meters should be the length then of our cord. Waves. Okay. We're going to talk about energy and intensity of waves as they travel. Okay. So energy of a wave is proportional to the amplitude, or the square of the amplitude. Can anyone describe to me what the amplitude is?
From the crest or trough to the center.
Exactly. The distance from either the crest, to the equilibrium, or the trough to equilibrium. Okay, the distance from equilibrium to its maximum points. So when we talk about intensity, it's this capital I. Intensity is going to equal the power over the area that the wave covers. And we remember our chapter on power a little bit? Kind of. Power equals work over time, or energy transformed over time. I'm going to show you a little bit better equation for this one in just a second, so we can compare some intensities of sound waves. But again, this is our intensity is proportionate to the amplitude squared. And when we solve for intensity, our units are joules per meter squared seconds. All right, let's look at a three-dimensional kind of version of this wave. Can we think of any times where we'd see three-dimensional, like a wave that spreads out in a three-dimensional pattern, like a spherical pattern? A bomb is one, right? If you have an explosion and the waves carry out three-dimensionally, what other ones? An earthquake, yeah, maybe. A rock dropped in water would give us kind of a circular ripple effect, but not necessarily a three-dimensional ripple effect. Okay? Yeah, sound would be one. Okay? As I speak, it echoes throughout the entire thing. Okay? All right, so let's look at this relationship between the intensity and the distance that we are from its source. Okay, so this radius right here is going to be the distance that we see from its source is going to be proportional to its intensity. So this equation right here is the one we're going to look at to be able to compare the intensities of these sound waves. Okay, so as dependent upon where they are from the source, we're going to be able to look at the intensity of that wave in comparison to basically where it starts. Okay, so if we're at two different points away from our source, we can look at the proportion of intensity of those sound waves. So we're going to look at the effect of the intensity of a sound wave that's 3 times further away from the source. Okay, so if you're 3 times farther away from the source than somebody that's right at the source, what is the sound wave intensity basically at that distance? Okay, so we're going to use that equation that we just looked at, we just learned. Which was I1 over I2 is equal to R2 squared over R1 squared. Okay, that was the equation that we just looked at for the proportions of these intensities based on its radius. So if we're looking at the intensity of a sound wave that's 3 times further away, are we going to be solving for I1 or I2? I2, that's what we're going to be solving for. Okay, so we want to end up looking for I2 here. And if we know that the radius is 3 times further away, which of these radius do we need to change? R1 or R2? R2, and we're going to change it to a what? Just to a 3, because we're looking at 3 times that initial radius, okay? So we're just going to keep it here. I1 over I2 is equal to 3 squared over 1 squared. All right, and our initial radius can just be 1 squared because we're looking at the proportion. Okay, so we want to know basically the distance here, or the difference, I'm sorry, between the first and the second radius, okay? So that leaves us with I1 over I2 equals 9. All right, so if we want to solve for I2, how do we get this equation manipulated to solve for I2? Yeah, we could just switch these two. We can just switch these 2 places. You'd multiply I2 over, multiply O2 over, and then divide by 9. We can switch those 2 places. So that means I2, or the intensity of the sound wave at the second location, would be equal to I1 over 9. Okay, so somebody talk through what that means.
I2 is 1/9 of I1.
Exactly. I2 is going to be 1/9 the value intensity of I1. Okay, so the intensity as you move 3 times the distance is only 1/9 of the intensity as you're at the source. Okay, so the farther and farther you move away, you're going to start seeing a very, very big difference in the intensity of that sound wave. Okay, so even though you're only 3 times farther away, you can only hear 1/9 of what the people up front are hearing.